Hi folks, the previous episode in the microcontroller tutorial series made you think that I was completely crazy, like connecting analog input to a GPIO pin on a microcontroller, which is configured as digital input. I can do even better than that. And what I want to show you today is what happens if you don't connect a microcontroller pin at all. Leave it floating. The effects you get there are really strange, really weird. And they make things depend not only on the microcontroller you use and the tolerances and whatever, but it actually makes things depend on the weather outside or the clothes you wear. And yes, I actually mean that. But before we see why things happen and how to deal with them, let's just give it a look, because this is so crazy you just have to see yourself. Let's take a look at the bench. And here you see the same setup as we've used before, except that I didn't bother to connect the microcontroller input to anything. And you see the PIC decides to turn the LEDs on. Basically means it reads a 1, sort of. More about that later on, whereas the MSP430 and the 80 mega don't do anything. And now let me just try if this works, because sometimes, for example, the PIC is ticklish. You see that? It's actually starting to flicker if you tickle it. And no, that's not a trick of the camera. It actually works, and I really hope you can see that. I can't tell from my monitor on the camera. With MSP430, you get even just near it, and it suddenly reads ones. Similar thing with the 80 mega. But to make things get really weird, it takes a plastic ruler, or historically a glass rod, and some old fleece sweater, or cat fur, as the old textbooks say. You rub the ruler with the fleece, and then you just don't even get anywhere near the microcontrollers, and all sorts of things happen. Now, is that cool? And yes, this is basically electrostatic, because as the microcontrollers are not connected, they get all of a sudden kind of sensitive to electrostatic fields. Another thing, let's see if this works. I have a jumper wire, not connected to the 80 mega, and it reads once. Pull it out, it gets even brighter, or it turns off, or whatever. And let's see if this works. You see what the PIC does when I touch the other end. Weather must be getting better again. This doesn't always work. And if you think these effects are strange, actually you stand up, sit down again, try again. Behavior might actually change. So what this basically shows, leaving an input unconnected, leaving it floating, is actually asking for all sorts of strange effects that are really, most of the time, undesirable. Well, unless you actually want to show people some strange things. To understand what's going on here, I have written a bit of a new program which just counts the number of times that the input on a microcontroller changes. And that's actually interesting, because it shows another effect related to this. I'll put it on the forum, but right now just let me install it. And here we go, and you see the PIC is actually counting. So it sees things change, or the input change. And if you take a stopwatch and figure out how often the leftmost LED changes, you can figure out that it's receiving input changes at a frequency of about 50 Hertz. Big surprise. Why 50 Hertz? Because that's what you get out of your AC mains out here. So the PIC is actually susceptible to whatever it receives from the mains lying around here on the bench, and possibly even further away. Similar thing with MSP430 and the 80 mega. And you see if there's anything coming close enough to it, it works. And yes, using a single-ended wire just basically works as an antenna. Doesn't have to be 50 Hertz, can be different effects getting into the equation as well, but this is really kind of what happens. And yes, when it comes to affecting the PIC, when I only do things to the 80 mega, that could actually be because they are fed by the same power supply and there's some sort of high frequency stuff going on there as well. So the first thing to learn from this is leaving an input floating is actually not the very best idea. It also shows that microcontrollers by default do this. And there's a question there. Why do they do it? Because it saves power. If you don't use the input pins and don't actually start to flicker LEDs or anything, you just leave them floating and minimize the power consumption, which is a big topic for microcontrollers, so big that we actually have to see about that another time when we have a bit more background. But there is something else where this is important, and that has to do with the toggle switch we've used in the previous episodes. So far we've just used the switch to connect the output pin of the switch to either VCC or ground. The switch is called a single pole because it has one output, double throw because it has two different inputs switch. However, what happens if we don't have something as nice as this? And this is not actually as nice as you might think, as we'll see in a moment. What happens if we have mouse pianos, which are dip switches, everybody here calls mouse pianos, which are just opening or closing a contact between two pins. So in the open setting, it's just leaving an input floating. Similar thing, I have this little push button, and yes, it has 4 pins, but that's just for mechanical reasons. It's just another one where it's just open or closed. Technical term here is these are single pole because they have one pole sticking out, single pole, single throw. This is double throw, these are single throw. They have one position where they're connected to anything. And yes, there are also some where you have a center position where they're disconnected and all sorts of weird and wonderful things. But what happens if we have to deal with these? Why would we have to deal with these? Well, sometimes our input just works like this. And these single throw switches and push buttons have a number of advantages. They're simpler to build. So they're cheaper, they're smaller, and they're more reliable. Or any combination, whatever of these. And we have to deal with these. Question is, how can we do this? Here's what we've used so far. We have our microcontroller with an input. There is our current limiting resistor, which is optional, but we might as well put it in. Talked about that in the previous episode. And yes, first off, don't be afraid of using schematics. They're just a short notation, make it much easier to figure out what's going on once things get a bit more complicated. I'm still amazed by people actually using fritzing or whatever to make drawing of whatever they do on their breadboards, and believe that people can actually understand that more easily than anything like this. Anyway, this is a resistor. This is the international symbol. Americans might actually find something that looks slightly different. Americans frequently draw resistors like this. Same thing, just different language. And this is a switch. Big surprise, it almost looks like one. And this is the output of the switch, and we can connect either to ground or VCC. That's what we've used with these toggle switches we've seen before. However, problem is, what if, say, this throw doesn't exist? In the lower position, where we connect the input to ground, everything is fine. But if we open the switch, we have a problem, because then we have our input on the microcontroller floating, and you've seen that's not a good thing to have. And the trick to deal with this actually goes like this. I'll try if I can draw that while you're watching. What you do is you take a fairly high value resistor and connect that to the input. You could actually connect it here as well. Might even have a couple advantages, but you'll see in a moment why I connect it straight to the microcontroller. When we do this, oh, hang on, this is important. Microcontrollers are using field effect transistors. They're CMOS based or whatever. Their input has very, very, very high impedance or resistance. So there's very little current going in here when they connect to anything. We're talking in the order of single-digit microamps or so, possibly even less, depending on what you buy and what input pin you use and whatever. Now, when we close the switch, connect this to ground, what we have here is a voltage divider. If we take value something like 10 kilo ohms here and our 470 ohms here, you get enough of a voltage here to make the microcontroller reliably read this as low. If, however, we open that switch, what happens is, well, there's no current going through this resistor, so there's no voltage drop. There's very, very, very little current going through the upper resistor. So we have very limited, very low voltage drop across the upper resistor. Basically means this is reliably read as high, because what the input sees is, for all practical purposes, VCC. And that's pretty much all there is to it. This is called a pull-up resistor. We could also do things differently if we removed this throw and brought that one to VCC back again. We could have a pull-down resistor. Let me get rid of this. We could do the same thing down here as well. Works just the same. And with this, we can actually make sure that even if the switch is open and we have an otherwise floating input, we get a reliable input voltage on our input pin. That's pretty much all there is to it. And I'd say we'll give it a try on the breadboard. Hang on. Since the PIC here is nice enough to keep flickering all the time this time, I've seen the others do it before. Here's our dip switch. Oh, actually, let's not use the dip switch, but let's just use the push button here. Makes it kind of nicer. Whatever. First thing we need to do, we need to connect one end of the switch to, let's say, VCC. And then we need our current limiting resistor on the output. And connect that entire thing to the input of the microcontroller. And with this, as soon as we press the button, the flickering stops, because now we have the input pin connected to VCC, to high. Let go, it starts flickering again. How can we make it stop flickering or counting? This is a 470 ohms resistor. I've got a 10 kilo ohm resistor. Makes sense. You can use 100 kilo ohms if you want. Doesn't really make a difference. If we now can use that to connect our input pin to ground, you see the flickering stops. And every time we press the button, you see that gets counted by the microcontroller as an input change, but it doesn't do any flickering, no matter what we do. And that's actually a good thing, even better than with these double throw switches, because a double throw switch has a problem. Despite the effort the designers of these do to make sure that you can't really put it into a standard position, center position, you can do it, but they're spring-loaded such that they switch rather quickly from one throw to the other. But there is a very short period when you switch where either the output, the center connector here, is disconnected, and we see the flickering again on the microcontroller, or we actually short the two inputs. And that's for real-world devices, not for theoretical things, really. But what that means is either we start the microcontroller to flicker, or we short its power supply, or whatever, and create all sorts of trouble that way. So it actually makes sense to use a single throw, switch, push button, whatever, we can get away with it. This isn't a disadvantage. All it needs is one pull-down resistor. And that's it, really. Well, except that there is more to it, of course. As you see, I've connected the pull-up resistor here straight to the microcontroller rather than to the switch. Why did I do that? Because a lot of times you actually have a pull-up resistor or a pull-down resistor inside the microcontroller. You don't need a physical resistor here. All you have to do is tell the microcontroller, please enable this. And let me draw it in here. Basically, we have our pull-up resistor built into the microcontroller, connected to the input. All we have to do at this point is figure out how to enable or disable them on our microcontrollers. And support for these things depends on the particular microcontroller. You'll see in a moment that the PICs only have pull-up resistors on some pins. The Atmels have pull-up resistors on all pins. In either case, you have to enable them as needed. Whereas the MSP430s have both pull-up and pull-down RINs, and you can enable either one or leave the input floating. And there's yet another question: why would you want to leave the input floating? It saves power. And if you have an input source that is high impedance, has its own equivalent series resistor or whatever, resistance or whatever you want to call it, then actually using the pull-ups or pull-downs in a microcontroller, they might be the wrong value, or they might actually affect whatever you read from them. So there are strange situations where you actually have to use an external resistor with a very high value or particularly low value or whatever. But most of the time, what the microcontrollers provide is perfectly sufficient. Okay, so the only thing that we have left to do is take a look at what the computer does. Now here's the cheat sheet that I've started, I don't know, episode 36 or so, and this is still what we have. Our information is already in there. And let's go to the last page, general purpose I/O. Make this actually readable. And in here you see there's a table plus some notes explaining things in more detail in case you want to look things up and don't want to watch a video again. And here's a section that has to do with pull-up, pull-down resistors in the microcontrollers. By default, all three microcontrollers we're using so far, input is floating, so saving power, yes, but we have to deal with things as they come. In some cases, there's some sort of global pull-up control. With the PICs, let's get there. With the PICs, there is a macro referring to a single bit in a configuration called not_RBPU, register B pull up. If we set that to 1, we disable the pull-ups for register B globally. If we want to enable an individual pull-up for an individual input pin, there's the WPU B in our case, and then whatever bit we want to mask out. We set that to 1, And once again, the colon, whatever notation I use here, means that's a specific bit I in a configuration word or byte or whatever. What does WPU mean? It's weak pull-up. And you can enable and disable pull-ups pin-wise using these registers. Important thing is that not all pins or not all inputs on the PICs actually are equipped with a pull-up resistor you can enable, and there are no pull-down resistors at all. They're simply none available. If you want to configure a pin as floating, you can mess around with the global pull-up, pull-down, or you can set WPUB:2 or whatever to 0. And once again, that's not available on all ports. With the Atmos, situation is somewhat better. There is, once again, a global pull-up control. There's a bit called PUD in the microcontroller unit control register, which you can use to disable all pull-ups on all inputs by setting it to 1. And by writing to port whatever, to specific bits, you can enable the pull-up on resistor. And I'm not particularly happy with this. Why is that? Because the port whatever thing is actually used for output elsewhere. It can get a bit confusing, and there are transition problems and whatnot. Anyway, if you set port B bit 2 or so to 0, you reconfigure the pin as floating again. Alternatively, you can mess around with the MCUCR bit PUD. With the MSP430, this is actually how I like it best. Similar to the AVR, you use the output bit to control whatever is kind of the default value of an input, if it's pulled up or pulled down. But you also have P, and for N being 1 or 2, whatever, REN. REN is resistor enable. So if you want to enable pull up or pull down, we have to set that P1 REN bit to 1, and then we use P1 out to decide if it's a pull up or pull down resistor. And if we set P1 REN bits to 0, it means these inputs are floating. Yeah, okay, that's how it looks in documentation. Does it actually work? Well, yes. Here's our header file we used before. Well, it used to be called GPIO input output. Now it's GPIO input pull-up output. And for the 80 mega, I've defined for the input pin I'm using a macro called float input, which just uses that MCUCR bit called PUD. And it means here, whatever you do, we control these on a bitwise level. And then I set port D bit 7 to 0, makes the input float, or I set port D bit 7 to 1, enables the pull up on the Atmel. And no, there is no pull down. On the MSP430, it's pretty much, well, as you've seen in the documentation, we can float an input by just setting P2 resistor enable to 0, the bit 2 in this case that we're using. And if we want to pull up the input, we set P2 resistor enable to 1, and then P2 out the bit 2 to 1, or for pull down to 0. And with the PIC, yep, well, as you'd expect, we said if you want to float input, we set the weak pull-up register B bit associated with our input pin to 0. And if we want to enable the pull-up, we have to make sure they are not globally disabled. So we have to set not register B pull-up to 0, and then we set the associated bit in PUB to 1. And again, there are no pull-downs available. And that's all there really is to it. And the biggest problem is actually that sometimes you have pull-ups but no pull-downs. Exception here are the PIC microcontrollers. And when it comes to the PICs, you want to be extra careful once again, because not all input pins actually have pull-up, pull-down resistors. Don't know why it's like that. I doubt it's because they want to save money. Might actually have to do with the fact that some input pins are considered for analog input or whatever. I don't know. Your guess is as good as mine. But, well, it's just something to watch out for, again. Okay, so much for today. And I'll link in the updated cheat sheet at the forum at www.stepladder-it.com/bivblog/50. Yoo-hoo! And if you have questions, comments, requests, complaints, whatever, come over there. One more thing. Messing around with electrostatic with live microcontrollers can actually make them less live than they were before. So if you play around with this, yes, there is a chance that you actually damage them. Be a bit careful. Don't overdo it with the glass rod and cat fur and whatever. Don't complain to me if you kill them. This is messing around with electrostatics near microcontrollers is generally a bad idea, but I guess now you've seen how to deal with the situation. Okay, so much for now. Hope you enjoyed it, and come to the forum if you want, and see you again soon. Bye.